All right, how's it going, everybody? We are here. I'm making this video today on Sunday, April 4th. Today we're going to talk about section 3.3. In general, this week, if you look above me here, 3.3 and 3.4, basically our goal of discussion this week is to talk about what happens when we have real, distinct eigenvalues. Fix my word right there. Real, distinct eigenvalues. And then in our next video, we're going to talk about when we have complex valued eigenvalues. So in general, remember that our basic goal in chapter 3 is for us to be able to generally classify the behavior near the equilibria that exists at 0, 0 for any planar uh, first order autonomous system of differential equations. And so we're going to talk about the bulk of our cases this week. We're going to talk about most of our kind of like fringe transition cases, our weirder cases, and our transition cases next week, as well as a little bit of a summary for those guys there. So we're going to do kind of a lot of math here today, but a lot of it's going to be kind of like validating some things that we already knew, kind of coming at lots of things from lots of different perspectives so we can see how everything kind of comes together here. In the last section, what we saw is that our eigenvalues and eigenvectors are telling us pretty much everything that we need to know about our systems. If we can find eigenvalues and eigenvectors that give us a general solution by using the linearity principle, they tell us where our straight line solutions are, which is really kind of our most primary thing that we need for graphing that helps us graph the entire rest of the phase plane. By knowing our eigenvalues, it's going to help us determine what our classification of the equilibrium at the origin is going to be. We did some of that classifying a little bit in the last couple videos, but those sections weren't really about those classifications today. And in our next video, we're going to that's going to be a little bit more of our main goal is saying what can we state in general is happening near the origin, given that we see these eigenvalues, sort of the characteristic descriptors of the linear system of differential equations here. The good news for us is that since we're only going to be discussing planar systems, remember this means two dimensions that we're looking at here, always only two variables, which we just keep on using x and y right here. What that means is that we're always going to have a characteristic polynomial that's quadratic. If we had three variables, a dx dt, dy dt, dz dt, then we'd be coming up with cubic characteristic polynomials in all of those cases right there. So the number of variables that we have in our system is going to give the degree of the polynomial it's associated with the characteristic polynomial. So what that means is, since our study here is focused only on our planar systems, we know that we're always going to have a quadratic characteristic polynomial. So the question that we should ask before we kind of get into this, like all this classifying that we're going to do, is ask like, what are all the possible pairs of roots that you could end up with for quadratics? How could these all kind of like, I don't know, be similar or be different from one another? Well, I know that I could get two roots that are both positive. I know I could get two roots that are where one is positive and one is negative, and I know I could get two roots where they're both going to be negative. Notice though that kind of skips over our zero cases right here. So zero and a positive or negative. Or maybe they're both zero. That's maybe a thing we should consider. Or maybe these are all cases where these are distinct from one another right here. Or maybe they're repeated. Or maybe they're imaginary. Maybe we're going to get some complex numbers in there. So there's kind of lots of different things that can happen. We can have two different positive numbers, two different negative numbers, a positive number and a negative number. When I say all these, I mean real numbers. We could get zero as one of the eigenvalues and then some other number. We could get both of the eigenvalues to be zero. We could get the two eigenvalues to be the exact same number, which is kind of weird then because it's not telling us any like new information. We're apparently going to get two identical eigenvectors then. And notice that if we have repeated eigenvalues, then we must have repeated eigenvectors. And if we have repeated eigenvectors, then that means that we only have one distinct straight line solution that we know. And we need to have two distinct solutions to come up with our general solution. So it seems like this repeated eigenvalue scenario is going to warrant a little bit more discussion. Similarly, if our eigenvalue is zero, then it's also going to make it a little bit more tough for us to use our general statement about general solutions. In this case right here, both being zero is going to be a not very exciting case, but we should state what's going to happen in that case there. And then imaginary solutions is a whole other animal out there, right? Getting non-real valued solutions. What does it mean to get imaginary solutions to a real valued problem? Can we make sense of that? That's what we're going to talk about in our next video on 3.4. So lots of different scenarios here that we're covering here in chapter 3. We kind of have our core of them, which we're going to talk about today, which is our distinct real eigenvalues that are not zero. Tomorrow we get imaginary. Next week our fringe cases will handle what happens when we get some zeros, what happens when we get some repeated eigenvalues. And what we're going to find is that those are going to sort of represent transitions between the others that we'll have discussed this week here. So our goal for today is to be able to draw phase planes and classify the behavior near the equilibria at 0, 0 in all cases where we find real, distinct, meaning different from one another, eigenvalues associated with our system. So let's go ahead and get started. We're going to just do a bunch of examples today. And again, this is going to be a pretty math heavy day, so you should take some pretty careful notes with this and write down all the things that you need to write down associated with this here. A lot of things we're going to see going on here today. So for our first example, what we're going to look to do is we're going to look at our like one of the simplest systems I can ever give to you. This is a great example right here to see if everybody's on board with what we've been doing so far. For me to say to you, you should be able to draw the phase plane associated with this system in about 10 seconds right here. This should be a really easy phase plane for us to be graphing right here. And here's the reason why. Notice that this is a fully decoupled system. The dx dt equation depends only on x. The dy dt equation depends only on y. So what that means to me is that if I want to draw this phase plane right away, then what I know is going on here is that on my x-axis and on my y-axis, I can tell that my x solution should be decaying. If x is positive, it gets smaller. If x is negative, it gets bigger. So I know that on my x-axis, I've got my arrows pointing in. Similarly, my y values should all be growing. If y is positive, then y gets bigger. If y is negative, then y is getting more extreme in the negatives out there. So I know that my y-axis is going to get our arrows moving out. The y-axis has 0 as a source. The x-axis has 0 as a sink right here. So what I'm kind of feeling out is that any other solution that exists out here in any of our quadrants is going to be somewhat mimicking the nearby straight line solution behavior. So if I'm starting from over here on the right, but a small y value right here, I feel like the nearby straight line solution is going to suggest that I'm going to do similar behavior, move to the left, but notice as I get closer and closer to the y-axis, it's going to say that I should be moving up. So I'm anticipating getting some solutions that are going to do some stuff that look like this in our kind of in the space out in the quadrants out there. Remember that because this is an autonomous system of differential equations, that means that our solution curves are never going to cross one another. So you should also notice in these cases right here, since we're moving perfectly horizontally and vertically on the x and y axis, that means that no solution could ever cross the x or y axis. If you ever hit the axis, you're staying exactly on the axis. And so we're never going to have solutions that cross that axis out there. So let's go ahead and do our eigen analysis associated with this guy. Let's find our eigenvalues and eigenvectors. Let's state a general solution. I think I've already got the phase plane. I want to see if my phase plane agrees with the solution that we're about to find here. And then we'll give a name to this guy, since I don't actually think we've named this behavior associated with the equilibria that's associated at the origin right there, right? We can see at the origin 0, 0. Has 0 for dx dt and 0 for dy dt, so 0, 0 is the only equilibria here. So 0, 0 is only equilibria. I'm going to say the phase plane is easy because you just graph the two phase lines first, since this is a fully decoupled system, and then you're just kind of filling in the spaces out here by generally following the behavior nearby of the nearby straight line solutions that I think I know about without actually doing any math. So let's go ahead and do our eigen analysis with this guy. So dy dt equals, it looks like our coefficient matrix here is -3 on the x term, 0 on the y term, 0 on the x term, 2 on the y term, and this is times our y vector, which remember is just xy as a vector right there. So this says to me that my A matrix right here is -3, 0, 0, 2. So what we should remember from the previous class is to find eigenvectors, or find eigenvalues. To find eigenvalues, we want to set the determinant of A minus lambda I to be equal to 0. That's the determinant of the A matrix minus lambdas on that main diagonal where our 1s would be for the identity matrix right there. So I'm going to get a -3 minus lambda, 0, 0, 2 minus lambda. That should be equal to 0. I'm going to do the thing that I always do with this, since I'm always subtracting lambda, but I always like lambda because it's my variable to be my first term in my quadratic stuff that's coming out right here. I'm going to factor a negative out of the first and factor a negative out of the second when we do the multiplication. They'll cancel together. They'll cancel together. This should be leaving me with lambda plus 3 and a lambda minus 2. So this is the down diagonal minus the product of the up diagonal, minus 0 equals 0. So it looks like we're really just getting this quadratic equal to 0. I can easily see that my eigenvalues are going to be 2 and negative 3. And one thing that you should notice real quick here, for those of you that haven't taken linear algebra, anytime that there's zeros on the off diagonal, we're always going to get that the main diagonal is exactly the eigenvalue. So any diagonal matrix where only non-zero the only place that there are non-zero values is on the main diagonal, then those values just are the eigenvalues. And we can see that we got 2 and negative 3 to be our eigenvalues in this case right here. So I've got my eigenvalues. Let's go ahead and find my eigenvectors to go with these guys. Now I would like to set up my a minus lambda I situation and find what vector causes us to actually get that stuff equal to 0 right there. So I want to have my, remember my general case right here. Let me write this like this, is that we should have a times a vector equals lambda times a vector. So we did our subtraction and we factored. And so we're trying to satisfy this final statement right here. I've found what my lambdas are. I know what A is. That's my A matrix. I know that I is the identity matrix. We just want to determine a vector V that makes this true. So A minus lambda I, that's this guy that we're looking at right here. So I'm going to evaluate, I'm going to check this guy out at both of our lambdas. So when lambda is equal to 2, we're going to get that A minus lambda I right there. It looks like we're going to get a negative 3 minus 2. 0, 0, 2 minus 2 times xy equals 0, 0. That's going to lead me to the statement negative 5, 0, 0, 0 times xy equals 0, 0. Remember, the thing that you should anticipate with these always is you should always anticipate that only one of the two lines is what you need for this. If there was ever two distinct pieces of information that you were getting out from each line right here, then that's going to be a guarantee that you did something wrong along the way. Notice that our second line right here says 0x plus 0y equals 0. Well, that's true for any values of x, y. That's not really helpful. What I'm noticing here is that I can come up with some better relationship right here. It looks to me like I need negative 5 times x plus 0 times y to be equal to 0. What that says to me is that y can be anything as long as x is equal to 0. So I'm going to find the eigenvector xy to be, I need x to be 0 so that we get 0 times negative 5. Then y can be anything that it wants to be. In general here, I like to pick the number positive 1 because remember, any constant multiple of an eigenvector is also an eigenvector. So if you said that your eigenvector here was 0, negative 14, you are also correct right there. That's it. It's perfectly acceptable. It's just that nobody would ever say that. We're kind of looking for our simplest possible way to express the a general representative of, maybe I would say, the eigenvector family, all constant multiples of the eigenvector right there. But again, you should verify for yourself that if we let xy be 0, 1, that will make this equation true right here. And the really important thing is that we just need the 0 in the x slot, so that 0 times negative 5 is going to be 0 right there, because we couldn't come up with any meaningful components for the y to cancel it out if it wasn't right there. So we found our first eigenvector. Now let's go ahead and find our second eigenvector. I should probably call that lambda 1 right there. Let's do the same thing again here, but let's use negative 3 as our next lambda value here. Lambda 2 is negative 3. And in this case right here, again, my a minus lambda I is now going to be negative 3 minus negative 3, 0, 0, 2 minus negative 3 times xy needs to be equal to 0, 0. We're looking for that vector xy to be our eigenvector. And in this case, you can notice that negative 3 plus 3 is 0 right here. So we're actually getting, notice this is like the exact same scenario right here. Almost the exact same scenario as our previous eigenvalue eigenvector pair here. Now notice here we're going to get 0 times x plus 5 times y needs to be 0. So in that case, it says to me y is going to have to be 0 to zero out the 5. X can be anything it wants because it's going to get multiplied by 0, and collectively that stuff will in total make up 0. So this is going to say to me that xy being equal to 1, 0 is going to be my second eigenvector right there. And I'm picking 1 for x because 1 times 0 is 0. I'm picking 0 for y because 0 times 5 is 0, and those two things add up to the 0 that I have in the lower slot on my solution vector over here, right? And again, if you would have picked 49, 0 as your vector, you are also correct because any constant multiple of an eigenvector is also an eigenvector. So it looks like what we found here is that with our A matrix being negative 3, 0, 0, 2, we found lambda equals 2 and negative 3. I'm not going to write it that way. I want to make sure that I lump together my eigenvectors and eigenvalues. So I'm going to say lambda 1 equals 2 goes with eigenvector 1, which was 0, 1. And we found lambda 2 was negative 3, and that is partnered up with eigenvector 2, which we just found to be 1, 0. And this allows us to write our general solution for this guy, which is our y of t is going to be equal to, and remember that this is our x solution and our y solution, are exactly what we knew them to be up here. And by the way, just like realize that all this math was stuff that we didn't really need to do. We learned how to solve this guy like literally on the first day of class. You knew how to come up with the general solution for this. Literally our very first video of the entire semester. Here, all you're doing, this is separation of variables right here. You're going to divide the x term over. You're going to get a natural log of x. You're going to exponentiate both sides. You're going to get e to the negative 3t for the first. You're going to get e to the positive 2t for the second, including a constant coefficient coming out from integration right there. We knew these solutions just from separation of variables from day one of this class right here. So remember that we're always going to be getting here lambda 1 k1 e to the lambda 1 t eigenvector 1 plus k2 e to the lambda 2 t eigenvector 2. And that for me is going to be k1 e to the 2 t 0, 1 plus k2 e to the negative 3t times 1, the vector 1, 0. And again, remember that this is really a like sort of two rows of solution right here, where the top part of it is the x solution and the bottom part of it is the y solution right here. And so recognize here that for this first term here, k1 times e to the 2t times 0 is 0. But we do retain the second component right here, which is k2 e to the negative 3 times 1 is just k2 e to the negative 3. Similarly, for the second part down here, adding together the bottom two parts, the second part on the bottom is just 0, so we can ignore that. The bottom part over here has 1 times this stuff, so we just get one copy of that. So we're just getting k1 e to the 2t down here as our x of t, y of t solution. This is again, I'm going to say it one more time. We literally knew how to solve this one on day one of this class. This is just separation of variables could have gotten us exactly right here, since this was a completely separable differential equation right there. All right. So we technically didn't need to use any of our eigenanalysis to make this stuff happen right here. We kind of already had access to this one right here. It's good for us to see that our eigenanalysis does agree with our very basic ideas of separation of variables. Again, the whole point of this, though, is that most of our systems of linear differential equations are not fully separable like this, are not fully decoupled, and so we usually can't use that type of technique in this scenario here. However, so let's state our classification here. So let me say here we had lambda 1 was 2, lambda 2 was negative 3, and our phase plane was, and we had a sink on the x-axis and a source on the y-axis, and our solution is doing some swooping over in our quadrants out here. So you should notice that the thing that's a little bit weird about this is that this is sort of like a half sink and a half source, right? We're sinking along the x-axis, we're sourcing along the y-axis right here. But it doesn't really seem like solutions are, it does seem like solutions along the x-axis do go to 0, 0. All other solutions get pushed to a y value of positive, negative, infinity. All right, so maybe we can make some general statements about this guy here. Um, for all initial conditions of the form, x0, y0, right? Initial condition, so at time 0. I want to make a statement about the x-axis values right here. So if our x value is whatever it wants to be, but our y value is 0, then the limit as time goes to infinity of x of t, y of t. So this is saying, given that your initial condition is some generic spot on the x-axis, what eventually happens to your location as time goes forward? You're going to go to 0, 0, right? This is our x-axis statement right here. Then we can also say, for all other initial conditions, not on the x-axis, what can we make a limiting statement about here? Well, I think here, as time goes off to infinity, right? So this is saying, if you start anywhere other than the x-axis, what eventually is going to happen to your x value and your y value? Well, let's just do these one by one here. What eventually happens to your x value if you start anywhere other than the x-axis? What is your x value eventually going to be? And it looks like here what I'm seeing from all the arrows that we've drawn here, our x values are always moving closer and closer to the y-axis. It looks like our x values are always going to 0 here. What is eventually happening to all of our y values, given that you don't start on the x-axis right here? Well, it looks like all of them below the x-axis are all going to tend down forever to negative infinity. All the ones above are going to tend towards positive infinity right here. So I think I can say here at least a pretty generic statement here that we're heading off to plus or minus infinity here. So this is all other non-x-axis values right here. This is a good long-term description of their behavior. In general, whenever we have lambda, I should just say lambda 1 comma lambda 2 is plus and minus, a positive and a negative. We say the equilibria at the origin is a saddle. It's a saddle because on a saddle, there's a angle at which things decrease, but there's also a different perspective from which things increase. You should sort of be thinking like a Pringle, I think is the modern day version of the saddle right there. If you're at the dead center of a Pringle, then you know that you would climb upwards to get to the lip in one axis, but then if you rotated the Pringle 90 degrees and tried to do the same action, that would be your fastest rate of decline down the chip, altitude-wise on that individual Pringle right there. And so this is why this is a pretty good label, I think, for this behavior at the origin, where we have on one axis things are coming in, on the other axis things are going away. And it doesn't really matter. I said this lambda 1, lambda 2, and labeled these lambda 1 and lambda 2. It doesn't, I'm not really too worried about the whole which ordering did you number them in here. We had two distinct real eigenvalues. One was positive, one was negative. Therefore, the behavior at the origin is what we would refer to as a saddle. Some stuff going in, some stuff going out. And we can make general long-term statements by using some limit notation here about where any initial condition might eventually end up in the long run. It looks like things are all getting, in a sense, compressed horizontally and stretched vertically. Everything is going to move towards x equals 0 and let their y value tend off towards positive or negative infinity. A good thing for us to do here is to have a little bit of technology verify this stuff for us here. So I, over the weekend here, I kind of cleaned up my Runga stuff right here to get a much nicer version of the Python code that we've been running. So a lot of this stuff, I'm going to point out some small differences here. I'll make this available for you guys so that you can use this as well here. But this is going to be maybe a little bit more robust graphers. There's two major features that I have added to this to make this a little bit better for us. Or I guess 3 total different features I've added. One of them is just old that we didn't incorporate before. So I'm going to do the same first, and in fact I should, just to make sure everything's all cleared here. I'm going to restart and clear all outputs here just to kind of start this notebook over fresh. See, those things went to 0, all my outputs are gone. So I'm going to go just kind of briefly walk through this here since you guys have seen all this. I'm going to import the 2 libraries that we know that we need, NumPy and Matplotlib. Here, I'm going to do something a little bit different by when I define my equations right here. What I'm going to do for myself is I'm going to state my 2 equations, f and g, as exactly what the most generic thing, ax plus by, cx plus dy. And I'm going to just state my a, b, c, and d up here. The reason why this is nice is because this now looks to me like my A matrix right here. So it's a little bit easier for me rather than kind of screwing around ever. So now I'm never going to ever touch these, and I'm only going to change my A, B, C, D for my A matrix right here. The other feature that I added to this notebook is that rather than having one initial condition, this is now going to take in a whole list of potential initial conditions and graph the long-term solutions for all of them. So here I have my initial condition list, and it's a list of ordered pairs that are going to be all the starting spots for a solution to be graphed. One of my things that I don't like about our old Python solutions is it always just graphs one solution. I might want to see lots of solutions graphed on one thing. This still isn't as nice as like a point and click to generate a solution, but it's nicer than just having one. And you can see here is a place where in our next problem, I'm going to only want to graph one so I can look at it a little bit more carefully right there. So in that case, I'll just comment out that list and uncomment this list right here, just to kind of my way to kind of preserve some code. So let's go ahead and run this cell right here. Notice, by the way, I've already entered in the appropriate A matrix coefficients relative to the problem that we've got right there. So it knows our F and G appropriately. Now I'm going to go ahead and initialize my parameters and solutions list. The only thing that's new over here is that now I need a whole list of lists of X values and a whole list of lists of Y values right here. And that's because I have maybe a whole bunch of different initial conditions, right? So I need an XY list for all the 9 initial conditions that I've thrown in up there. The other thing that you should notice here is that I have 2 sets of them. I have the 1s and I have the 2s over here. That's because the other feature that I added into this plotting right here is doing both forwards time solutions and backwards time solutions. So that if a graph starts at 1, 1, I might see some part of the curve moving away, but I might see some part of the curve going towards the origin if we were to go backwards in time. We're now going to get both of those components in our upcoming graphs right here. So this is my like beefed up version of some stuff that you otherwise already remember. And again, here you can see all of my lists, all of the like tons of lists that I'm making, I'm sticking in our initial condition as that first thing in all those lists. So let's go ahead and run this cell here. Now I'm going to use our run-to-kata method. Once again, the only thing that's new right here, this is like exactly copied and pasted from before. The only thing that's different is that now I need to do all of our different lists right there. So this is all of our, you guys recognize all of this code right here. The only thing I've done is thrown all of that within a loop that says, actually do the whole run-to-kata method for all of the initial conditions. And this is all of our forward time solutions. Then I copied and pasted this entire block right here, and I said, do the exact same stuff again, but the one thing that's different is I said, by the way, make our time step a backwards time step instead of a forwards time step. So if our delta time was like 0.25 before, it's now negative 0.25, and that's what's going to help us walk backwards. Other than that, the rest of this code is identical right here. I'm just saving things into our list that I labeled as 2 because those to me are referencing all of our backwards time stuff. So I found all of my XY partner pair list for graphing in forwards time in the previous cell. Now I've found them all in backwards time. And now I can go ahead and plot all of our stuff. I beefed up our plotting also because I wanted to plot both the phase plane and all of our initial solutions here. That'll be helpful for us here in a minute. And what I've done for myself, and I just made this the title as my descriptor of how to read the graph, is I've made it so that our 1 lists, the forwards time stuff, is going to be a solid line. Our 2 lists is going to be a dashed line, and that'll represent all of our solutions going backwards in time so that we get a full curve rather than actually starting at a point. It's just going to be the solution curve that passes through that point that's right there. And again, this is just me kind of this is just a lot of copying and pasting. This looks like a bunch more stuff than what you've seen. This is me just copying and pasting together kind of lots of the things that we've done with graphing in the past. So let's go ahead and take a look right here. Hey, where's a bunch of my, didn't get a bunch of my forwards and backwards time solutions. How is this possible considering I just did this 5 minutes before I started this and make sure that this works? Okay, they're there all of a sudden now. So the thing that we can read off of right here is that the solid lines represent our forwards time solution. So I can see things like when we started at 1, 1, it does seem like in forwards time, as time goes to positive infinity, our solutions were converging on the y-axis. And therefore, you can see if we just flipped all the arrows on our graph into our backwards time stuff, then if we went as time goes to negative infinity, then we're instead sort of reverse converging on the x-axis right there. The only difference that you should see right here is notice that at 1, 0, since 1, 0 is on the x-axis, these are the ones that actually go towards the origin. So you can see that little bit of solid line that I've got right there. And again, I just kind of arbitrarily picked for there to be like a little grid of points near the origin right there because our goal is to classify the behavior near the origin in this chapter, right? So I just picked 9 initial conditions near the origin. I stupidly picked the origin, even though that point is always just going to stay at 0, 0 on all of our graphs, and 0, 0 is always going to be in equilibria. So I'm really just doing some wasteful computation there where it's doing the Runge-Kutta method, like all these steps and just getting 0, 0 for every single step because I'm dumb. The other thing that we can see over here is our individual solution graph. We can see that the x values in forwards time look like they converge to 0. Notice that this blue solid line is our forwards time stuff for our x values. The x values are all going to 0. That's like we said, all of these things are pointing in. You can see that all of our y values seem to be diverging off to positive and negative infinity in the forwards time as well right there. So this is actually 9 different individual solution curves all graphed over top of one another, but they're all almost exactly the same thing. You should notice our x and y, or our y axes here. Sorry, our vertical axis, I shouldn't call it our y-axis here. Our vertical axis has huge numbers. Technically, right around here at 0, 0, there's like our 1, 0, negative 1, 0, those kind of numbers. You just can't tell because 1 is not a visibly distinct number from 0 with this scaling on our axis over here. I'm not too worried about that for right now, though. This generally agrees with the stuff that we just graphed by hand. This does look like our by hand graph that we came up with a moment ago right there. And I don't know. I could change. I'm not going to change our axes. Well, I mean, I don't know. If I just change this to like 2.5s for all of these right here, then maybe our graph will look kind of exactly like our. Rerun it. There we go. This graph now looks a ton like what I just graphed for you guys. Putting arrows on this is like a monumental challenge, which is why I did my solid line for forwards time, dash line for backwards time from an initial condition given at a given point right there. So this feels really good to me. I feel like we kind of nailed it with that really quick graph that we just drew right there. And we shouldn't necessarily expect that it's going to be that easy, right? This is sort of like our easiest possible scenario right here. So let's go ahead and let's look at a saddle situation that's not as easy to discuss as the previous one right here. And in particular, what I'm going to want to talk about with this one is how do we know what the individual x of t and y of t solutions are going to look like if we didn't have technology to help us out with this one right here. So let's go ahead and do example 2. If you're obviously, all of you are watching this afterwards since I'm not recording this live right now, I would highly, highly recommend that you pause the video right now and perform all of your eigenanalysis and get all the way down to having stated your general solution based on your eigenvalues and eigenvectors, and then see if your solution matches mine. So please pause right now and do this problem. Find your eigenvalues, find your eigenvectors, find your general solution, and then let's go ahead and graph some stuff together here. All right, so here we go. I'm going to do this guy now. So I want to do my, so let's find my eigenvalues, and let's do my determinant of b minus lambda I is equal to 0. My determinant of 8 minus lambda, negative 11, 6, negative 9 minus lambda equals 0. That's going to give me lambda minus 8 times lambda plus 9 by factoring out a negative from each of those and multiplying them. We're subtracting 6 times negative 11. So it looks like I'm going to get, so what I'm noticing here is I know that I can't use factored form since there's an extra term, so I need to expand this term right here to try and incorporate the other constants here. Hopefully it factors. If it doesn't, we go quadratic formula. So save some space here. This is going to give me what? Lambda squared plus lambda, because I have a negative 8 and a positive 9, minus 72 plus 66 equals 0. Lambda squared plus lambda minus 6 equals 0. It looks like it does factor. Lambda plus 3, lambda minus 2. And I'm going to get that lambda equals 2 and negative 3 for this guy right here, which, notice, is exactly the same eigenvalues we got in the previous 2 and -3. We got 2 and -3 again. However, what I'm noticing here is that based on this B coefficient matrix right here, it does not look like we're going to get the same eigenvectors. It doesn't seem at all. And in fact, we had no way to solve this. So in our previous problem, we could have literally found that general solution on day 1 of this class. For this B coefficient matrix right here associated with our differential equations, we couldn't have solved this until like the last video right there. We have to do eigenanalysis to get at these solutions right here. We don't really have another route. So let's go ahead and find the associated eigenvectors right here, evex. So I'm going to we want to remember that our goal here is to set up our b minus lambda I times the eigenvector is going to be equal to 0. So we're going to do that for both of our eigenvalues. So eigenvalue 1 is 2. So b minus lambda I, and again, I always kind of am like stealing my work from before. I'm using this as my like visual reference right there. It looks like I'm going to get 8 minus 2, negative 11, 6, negative 9 minus 2 times xy equals 0, 0. I'm going to simplify, and I'm going to get 6, negative 11, 6, negative 11. And so, as usual, your check is it should be that you're getting only one meaningful piece of information out of this matrix form system of equations right here. We just got two equations that are identical to each other right there. So that's good. We got that redundancy in there. So here's one of these great places where strategy-wise, this is one of the good dumb techniques that you can always do to find your general solution for this guy. In this case, remember that what our goal is always to get 6 times x and negative 11 times y to be equal to 0. Well, what we can always do is since we're adding those together, is just pick the opposite numbers for each of them. If we did 6 times negative 11 and then negative 11 times 6, oh, excuse me, I guess we have to pick slightly different positives, negatives out there, but we can make these cancel just by getting 11 copies of 6 and 6 copies of 11, and as long as they're opposite sign, then 66 cancels with 66 to give us 0. So here, I'm thinking that a good xy solution vector for this guy is going to be, let's choose 11 for x so that we get 11 times 6 is 66. And then we'll choose 6 for y so that negative 11 times 6 is negative 66. And those two add together to give us 0, just like we want right here. So this is sort of like one of those dumb things where it's like when you're getting a common denominator with 1/3 and 1/5, you're just multiplying each fraction by top and bottom by the opposite fraction's number. That's kind of a similar thing going on right here. So it looks like this is my first eigenvector is our 11, 6. Let's do it for lambda 2. So negative 3. And this is going to give me 8 minus negative 3, negative 11, 6, negative 9 minus negative 3 times xy equals 0, 0. This is going to give me 11, negative 11. And 6, negative 6. Once again, we're getting redundancy in our system of equations right here. This is really equivalent to just x minus y equals 0 for both of them because this constant multiple business doesn't really matter. You just divide both sides by 6 because 0 divided by 6 doesn't matter. Divide both sides by 11. 0 divided by 11 is just 0 still. In this case, again, this is probably like our nicest looking case ever for solving this system of equations right here because positive 11 and negative 11 cancel out automatically if we just keep one copy of each. So I'm going to choose 1 for x and 1 for y, so that positive 11 plus negative 11 equals 0, and we're good. And that's true for both the top and bottom here, right? So 1, 1 seems to be my good eigenvector for our second guy right here. So we've got our eigenvalues, we've got our eigenvectors, and this allows us to state our general solution. Our variable vector, the capital Y vector right there, should be equal to k1 e to the 2t 11, 6 plus k2 e to the negative 3t 1, 1. I think that this one right here, because what I'm going to want to do in a moment here is kind of make some comparisons between these two guys. I still want to graph my phase plane and my individual xy solutions right here. Now that I've stated my general solution, I'm going to state my general solution also in its sort of like other format right here, right? This is our x of t, y of t solutions. Look like this. Now notice we have no zeros in our eigenvectors now, so we're actually going to get all 4 components popping out of this. So it looks like I'm going to get 11k1 e to the 2t plus k2 e to the negative 3t. I'm going to get 6k1 e to the 2t plus k2 e to the negative 3t. It looks like this is our general solution. It's our solution for x, and this is our solution for y down there on the bottom. So if I want to graph my phase plane, I can graph my two eigenvectors, are representations of my straight line solution. So graphing phase plane, my eigenvectors are vector representations or representatives of our straight line solutions. So what that means to me is I'm going to come over here and I'm going to graph the line that passes through the origin and passes through 1, 1, right? So there's 1, 1, and I know that there is a straight line solution that passes through this and the origin right here. So it seems like one of our lines is going to be our 1, 1 line right there. This is our, I guess I would call this our V2 line right there. It's our second eigenvector was 1, 1, and here's the line representing it. You should also notice that on this line, this was associated with a negative eigenvalue. You should notice that this represents this stuff decaying towards 0 as time increases if you start on that line. And so I know that on this straight line solution, we're going to get decay towards the origin here, because it has a negative eigenvalue right there. As t gets bigger and bigger and bigger, this component of the solution goes to 0. That's exactly what I'm seeing here. On the other hand, we've got the solution 11, 6. So 11, 6 is going to be, somewhere like over here. Again, this is part of a straight line solution through the origin. So I think it's going to be looking something a little bit like this. Not bad. I'll erase my dot, but I think that was a pretty good estimate for this guy right here. I'll go ahead and call this our V2 or our V1 line right there. That's associated with our first eigenvector. That's our 11, 6. And more here, I can also tell that as time goes to positive infinity, you should notice that this is this is representing growth. E to the positive 2t says as time gets bigger, this is getting to be a larger and larger number. We're going to be experiencing growth along this straight line solution right here. So I am getting growth along this straight line solution. Right? It's growing away from the origin right there. So notice that once again, our equilibria at 0, 0 has two straight line solutions passing through it, one that's growing and one that's decaying. So that says to me we're going to be getting a saddle, right? So I'm going to say lambda equals 2 and negative 3 implies saddle at the origin. So there's our classification. We've got our phase plane sort of drawn right here. I now need to ask myself, what do I think that the other components of this look like here? Well, again, I think I can kind of generally say anything else is going to have to vaguely follow the eigenvectors that are nearby it, because we don't get solutions intersecting one another. So for example, if I were to start down here, I'm going to vaguely do what this guy's doing, but it looks like which is going towards the origin, but it does look like I'm never going to quite actually get there. It looks like I'm going to get swooped out by our other eigenvector eventually. So I'm expecting to get some stuff that's going to look like this here, and a similar one on the other side over here. Over here, I expect that any solution on the inside is going to have started closer to one than the other, and it's going to follow a nice swoop just inside of this guy right here. And similarly, oops, well, okay, that's fine right there. I'm trying to draw mine in the direction I'm going to put the arrows on it. And it seems like there's also going to be solutions in there that are going to be, if it's nearer to the one going in, it's going to go in for a while. If the initial condition is nearer to the vector going out, it's just going to go straight out from that region itself right there. So I think this is a reasonable good guess as to what my phase plane looks like here. But the other thing that we want to do is attempt to graph our individual solutions right here. And here's the thing that I'm going to do to help myself out. The thing that's really interesting about this guy right here is that it's got both parts from both of our solutions in both x and y right here. The other thing that's really interesting about this is that we have one positive eigenvalue, which gives us a growth exponential, and one negative eigenvalue, which gives us an exponential decay. So what that says to me is I think what's going to be really helpful here for me is to think about both positive and negative times. So one thing I would ask you is, what do our x and y solutions look like at time 10, for example? And stop and think about this for yourself. At time 10, what would be like a simplification of this expression right here? Well, I'm noticing that at time 10, these two terms are going to have numbers like e to the negative 30 tacked onto them. That's basically zero, right? So I'm thinking at time positive 10, this is really the only meaningful contribution that we're getting to these solutions. On the other hand, if we're thinking about time negative 10, right, if I'm going backwards in time to look at the other direction of my solution here, at negative 10, the first two terms are going to be negligible. We're going to get like e to the negative 20 power. That's basically zero. But when I plug in negative 10, it looks like we're going to get positive exponentials here. There's actually going to be some meaningful contribution to the value of x and the value of y. So basically what this is saying is for positive times, only one term matters. And for negative times, only one term matters, and it's the other term when we're considering these solutions here. All right, so I think that this is a good description of what our solution curves look like near the origin, but far away from the origin, or I should say far away in time, this is sort of misleading because one of these terms is eventually going to be zero, whether you go off in the future or you go off in the past. And I think that's kind of, in a sense, worth saying right here. All right, so, well, yeah. I'm going to say our x of t, y of t solution is going to tend towards, and so what's happening here at positive time? So as our times get really, really big, it looks like these two components are essentially going to zero as time gets very big, and all that we really have left is these two guys right here, 11k1 e to the 2t, and 6k1 e to the 2t, right? That's the only parts that are really remaining right there, right? That's as time goes to positive infinity. And what you should notice here is that this looks like x and y are just going to be a constant multiple of one another right here. It looks like if you multiplied y by 11/6, you should be getting x right here. So while these are both exponential curves, so this is, I should say, both exponential curves with x being 11/6 as tall as y. Right? So I think that's going to be one helpful part for my overall individual solution graph right here. So let me get this started over here. So this is saying, as we head off into forwards time, I'm seeing that two of the components out of the four components of my general solution are going to go to zero. These two are going to essentially go to zero as time gets really big. These two are going to remain making a meaningful contribution, but they're both almost the exact same exponential curve. One's just off by a constant multiple from the other. And so I'm thinking here to myself that we should be experiencing some exponential growth. Oop, I'm gonna back out real quick right here and do this in color. I'm thinking that we should be experiencing some exponential growth where the x of t solution is just going to be a little bit above the y of t solution, but otherwise doing the same thing where each height is there. And notice this is almost just like x is twice as tall. That's like almost what we've got going on right here. Now on the back half of things, what I'm expecting to see is that as time goes off into the negative infinities, what are we going to see? Well, as time gets to be very negative, right? If we go in the other direction right there, if I try and graph the left-hand side of my individual solutions, then you should notice that when time becomes a large negative number, our first two components here that we kept before, those are now the things going to zero. Like e to the negative 20 is essentially zero right there. And what we're keeping is we're keeping these two terms right here, our exponential decay terms. So k2 e to the negative 3t for both x and y. It looks like our x parts and our y parts are both exponential decay functions that are going to exactly match one another. All right, so it looks like I'm getting here K1, or wait, that was K2, right? Yeah, K2 e to the negative 3t for each of them. K2 e to the negative 3t and k2 e to the negative 3t. These are both exponential curves decaying to 0. And they should be the same. Now, I'm going to say approximately the same curve because we're sort of like zeroing out something that's not quite zero here, right? Like at time 3, we're getting like an e to the negative 9 for this. Well, it's not quite zero. It's still going to make like some little smidge of contribution right there. So I'm expecting that my x and y graphs are going to still differ like ever so slightly from one another, but they should be limiting towards being literally identical to one another right there as our times get very, very negative here. And I know that they're exponentially decaying to 0. So what I'm expecting to see right here is our solution curves here doing something where they're going to exponentially decay towards 0 in positive time. And similarly here for our y graphs, I think that this one, I'm going to do my best right now. This should be like, oh, hey, I'm doing a pretty dang good job right there. So I think that those are like basically our same graphs right there in our negative time graph right there. So this is one way that we can go about this, especially in saddle cases right there, going about doing this, because for every saddle, you should always have one positive and one negative eigenvalue right there. So for every saddle general solution, looking at forwards time, there's only one out of the two terms matter, and looking at backwards time, the other one out of the two terms matter, which makes it a little bit easier for you to make the general distinction between these two guys right here. So what I want to do now is let's do our usual thing and let's go ask technology to, oh, that was weird, double that up. Is that really, that's awful strange right here. Okay, so let's go ahead and kind of do our technology verification. So what was our B matrix? I'm going to throw this in 8, negative 11, 6, negative 9. So let's go back over here. Oh, by the way, I want to undo these changes that I made right here. Okay, so our B matrix in this case was 8, negative 11, and then 6, negative 9, right? Let me go double check that. 8, negative 11, 6, negative 9, 8, negative 11, 6, negative 9. Looks good. Okay, so let's go ahead and run through this guy right here. I am going to change this guy so that we just have this one initial condition right here. You should notice that based on the way that I wrote my code, it's always still going to expect there to be an initial condition list. So even though I'm only giving one initial condition, it's a single object. This is a list of length 1. There's one ordered pair in my list, but I got to do that just because I wrote my code to expect it to take in a list of initial conditions now. That's not that big of a thing to get over. But I just want to see one good initial condition so I can see our individual solution graph be correct here. So run it, run it, run it, run it, run it, run it, run it. And what do we got right here? Well, this isn't a very helpful graph for me right here, but what I'm really interested in, oh yeah, is our really nice graph right here representing, I even picked my blue and orange to make sure that these guys are going to match up together. What you can see is that we do have exponential growth as we move forward in positive time, where it looks like they're growing approximately equally, but the blue graph is a constant multiple of the height of the y graph. You can see going back to the left, and I know that you guys certainly can't see this, I can ever so barely see like little smidges of blue at the fringes of these dashes right here. The blue dashed line for backwards time certainly is there, but what you can see is that these are essentially equal to each other, even in the long run right here. So it does look like we nailed it right there on that individual solution graph right there by playing this. What happens as time gets to be a large positive number? What happens as time gets to be a large negative number? And recognizing that lots of the terms associated with our general solution were going to 0 in those cases right there. This isn't a very helpful graph because there's only one point in it. Let's go ahead now and add in all the initial condition points. So now what's going to happen is we're going to get a really difficult to read individual solution graph, but our overall phase plane is going to be a lot nicer now. So I'm going to switch back to doing our 9 different initial conditions right here. So let me go ahead and rerun everything as we do. And now what you can see, and now this is, again, a bit of a tight view of this guy right here. But what you can see is we do, in fact, have our straight line solution here. Because remember, 1, 1 was an eigenvector. So going from the origin to this upper right green point, that is 1, 1. So that we actually have one of our straight line solutions graphed. You should see that it should have been a sink along that 1, 1 eigenvector because we get the solid line from 1, 1 to the origin, and the solid line is forwards time. So in forwards time, it's decaying to the origin, and dashed line backwards time, it's moving away. And back over here, we did, in fact, have that our 1, 1 solution associated with eigenvector 2 was decaying towards the origin, as we're suggesting is happening here in our phase plane. The other thing that you can see is that we've got these like bowing solutions out here that are like a nice swoop. That's because these eigenvectors are almost doing the same thing, right? They're sort of just like meeting at this angle, and so we're going to get some swoops that are going to be the sort of the curvy version of that meeting and at an angle thing right here. So just as one quick little verification, we can see that the point at 1, at the point at 1, -1 right there seems to be moving up and to the right in forwards time. So we should be expecting to see the arrows pointing up and to the right for that guy. And when we go back here to look at what we graphed, yeah, I see that our guy that I wrote that's going through 1, -1 right there is in fact moving up and to the right as its direction right there. So I do strongly agree with the phase plane. And again, I drew this phase plane, and it's not because I graphed this before in Python, right? The reason I knew how to graph this phase plane is because I plopped down my two straight line solutions and I said, what must happen if no solutions are going to intersect with each other? Well, I know that all other solutions are just made up of linear combinations of the two straight line solutions that exist, meaning they're going to agree with them based on how far away from them that they actually are. The closer you are to a straight line solution, the more your vector is going to look exactly like that straight line solution. And so I'm sort of mimicking them with nearby curves to find what these other curves are going to look like right here. And I think the other thing, I guess we didn't really get any of these swoopy ones in our graph out there, just on where I placed my points. But again, with my code, I could certainly add some other initial conditions to maybe see some of those swoops in there. But we can see that this is already a slightly crowded plot right here. This is not the overall best visualization of this, but it's good enough for me to validate my by hand graph right there. All right. So that was a cool example right here. Again, we could not have solved this without our eigenanalysis based on the tools that we've got available to us right now. But based just on our eigenanalysis, only doing linear algebra steps right here, we were able to come up with a general solution to a system, come up with a phase plane, thinking about limits, the closest thing we got to calculus here, we were able to come up with our graphs of our individual solutions by thinking about the fact that exponentials, when we have positive and negative exponentials, one of them's going to 0 in positive time and negative time. So again, if you're kind of still confused on this one, go ahead and literally plug in, give yourself an initial condition like 0, -5, like I did in Python there, and go ahead and plug in t equals 10 and t equals -10 and numerically see what you're actually getting for these, and you will agree with the fact that we sort of assumed that a pair of these terms went to 0, once with forward time and then the other pair with backwards times right there. E to the -20, that is an outrageously small number right there. It's worth calling that 0 for our simplification for our graph right here. All right, so that was our like kind of better saddle example right there. We're still getting this sink versus source behavior. It's just a little bit harder to describe than we could with these limit statements that we had right there. So let's go ahead now and look at a slightly different example. Again, we're going to do the easy version and then a slightly more complicated version here, so that we can see sort of some comparisons. So here's another good place for you to pause the video and you to do the eigenanalysis yourself. You should be able to state the eigenvalues. And by the way, you should already know the eigenvalues. Look at the matrix. Why do you already know the eigenvalues? From the eigenvalues, you should be able to get the eigenvectors. From the eigenvalues and eigenvectors, you should be able to state the general solution. Based on the fact that we have sort of a special case right here, it should have actually been automatic for you to draw the graph immediately, except for one slightly confusing part. And so the thing that should be easy here is your axes. And the thing that should be a little bit tougher for you is deciding what do the curves look like not on the axis. And we're going to look at a little bit of a crafty way that we can answer that here. That will only sometimes work. And so let's go ahead and do this here. So again, you should do this yourself for practice right now. See if your work matches my work right here. So I'm going to say eigenvalues. And right away, what I'm going to say is they should be lambda equals -1 and -4 because we're on a diagonal matrix. And remember, a diagonal matrix meaning the only place that there are non-zero entries is on the main diagonal, the top left to bottom right diagonal. If that's the case, then that diagonal is your list of eigenvalues. Let's go ahead and actually do it right here. Let's go ahead and see determinant of c minus lambda I is equal to 0. This should be the determinant of -1 minus lambda, 0, 0, -4 minus lambda is equal to 0. This gives me lambda plus 1 and lambda plus 4 is 0. And what do you know? We're going to get lambda equals -1 and -4. Let's go ahead and find our eigenvectors. All I got to do is throw in each of these lambdas here, multiply that vector by, or matrix by the vector v, and find what vector does that for us here. So we're going to do lambda equals -1, and I'm going to see here that we're going to get -1 minus, I better be a little bit more careful right here. And I can tell you guys, there's always going to be so many negatives floating around out here. You got to be careful. This is -1 minus -1, 0, 0, -4 minus -1 times xy equals 0, 0. We simplify this guy. We're seeing we're getting 0, 0, 0, and -3 times xy is 0, 0. What this means to me is that we're getting x times 0 plus -3 times y, and we need to get out 0. So that tells me the y component is the thing I'm worried about being 0. So that tells me I need to make sure that y is 0. So xy, I need y to be 0, but notice x is already getting multiplied by 0, so x can be whatever it wants. It's going to be 0 either way. So I'm just going to go ahead and let that be 1. That's always my easiest possible number to choose right there, and I'll go ahead and call that lambda 1. In this case here, you should notice that lambda 2 is -4. Notice in this case, both eigenvalues were negative right here. Remember that eigenvalues are helping us describe our growth versus decay, and so hopefully you're down with the fact that this means that both of our straight line solutions are going to represent decay towards the origin, and therefore I am expecting all solution curves will experience decay towards the origin. So this one right here hopefully feels pretty natural for you to define as a sink, just by looking at the eigenvalues here. So we're getting an incredibly similar situation right here. It looks like I just need x to be 0, so that 0 times 3 is 0. Y, I don't care what y is. It can be whatever it wants because it's getting multiplied by 0 already to get us to 0 as our total here. So it looks like I need to be saying here that our x, y, I need x to be 0 to 0 out the 3. Y can be whatever it wants, so I'll make it 1, and I'll call that my second eigenvector right there. So I've got my eigenvalues, I've got my eigenvectors. It looks like our general solution then is going to be our y of t going to be equal to k1 e to the -t 1, 0 plus k2 e to the -4t 0, 1. And if I wanted to instead, I could write these sort of individualized. Both ways are typical to write these guys. There's not really one that's... It depends on the situation, I guess, but both of these are acceptable ways to write this final answer. Again, notice that when I'm looking for the top parts, there's nothing on the right. When I'm looking for my bottom parts, there's nothing on the left right there. Those are the things that are getting zeroed out. So it looks like I'm just getting k1 e to the -t and then k2 e to the -4t here. And so I want to try and graph our phase plane, right? So I'm going to say this, sort of easy, sort of hard. The easy part is that I know what my x and y axes look like here, right? And the reason that I know what my x and y axes look like is because remember that this is describing to us the system that just looks like dx dt equals -x and dy dt equals -4y, right? This is a fully decoupled system right here. It looks like if my x values are positive, then they're going to decay. And if my y values are positive, they're going to decay. It looks like the phase line for both of these is 0 is a sink. And so it's really, really easy for me to say, up, equilibrium at the origin, and both of our axes represent just decaying. What's not clear to me is what goes on out here. Right? So I'm really comfortable with this, but if all the other ones out there in space are going to be some curve that's some linear combination of these two solution parts right here that looks like this general equation right here, how are they curving towards the origin? I mean, one thing I could think to myself is that, you know, if everything's decaying towards the origin, one thing I might think to myself is maybe they're all swooping in like this. Right? Maybe there's something like this going on. Or maybe, instead, that with our sinks towards the origin on the axes here from our two phase lines being drawn in the same graph, maybe instead they're doing something like this. How do you know what shape these are going to take on? And the answer is, in this case, we can easily decide. In this case, we can easily decide. Because there's something a little special about this one right here. I'm going to say, given the solutions of x of t equals k1 e to the negative t and y of t equals k2 e to the negative 4t, is there any special relationship between x and y? Well, yeah. It looks like y is just the fourth power of x, give or take a constant multiple. I'm just taking the fourth power on e to the negative t to get e to the negative 4t, right? So what that says to me is up here I graph two potential situations. I feel very, very confident that it's actually this bottom situation right here because I know that all the remainder of the solutions out there should all look like the graph of x to the fourth, which is sort of like a parabola. It's definitely not a parabolic shape, but it's, well, okay, it seems parabolic. It's going to be that cup shape thing, but it's going to be a little bit boxier down towards the edges down there because that's slightly higher power. So this says all solutions not on the axes are going to look like y equals x to the fourth. So what I'm expecting to see then is sinks on the axes, because that's where we're looking at the individual solutions as if this weren't even a system of equations at all. This is just two phase lines from chapter 1. Then I know all remaining solutions are going to have to sort of have sort of this type of shape right there. Or, right, the constant multiples up could also work out right there because we don't know if K1, K2 are positive or negative. That would depend on the initial conditions that we might be plugging in here. But I feel pretty good that all of our other solutions are going to look like a x to the fourth, right? So maybe I would say y equals K3 x to the fourth, right? Some ratio out there. I would say that uh, y is proportional to x to the fourth. That's like just a constant of proportionality that's out there. So it looks like this would be our good final generic phase plane right here. And our goal, remember, is to classify. So I think I should make a classification statement that says when both eigenvalues are negative, we say the equilibrium at 0, 0 is a sink. All right, so let's go ahead and verify this in technology, and then we'll look at a slightly more complicated example, because the thing that's really nice here is we got to make this algebraic comparison right here, but absolutely that algebraic comparison is not going to work out all the time. So maybe we should say, what could we otherwise do to figure out what our other solution curves look like here? Because the really weird thing here is that it seems like as we get really close to the origin, our solution curves, not the straight line solutions, are going to follow in one or the other. And notice that in this case right here, I actually want to, before I go on any further, I want to point something out here. So let's see here. Negative 4 is a much stronger decay, all right? And this was our 0, 1. So this was our y-axis, and this was our x-axis right here. So I think that I can call 1, 0. So 1, 0 is on the x-axis, and that's the weaker of the two eigenvalues. It's the one that's not causing as rapid of decay. It's only e to the negative t instead of e to the negative 4t. It's weaker decay. E to the negative 4t is much stronger decay, and that was our y-axis. But it seems like things were following in the x-axis here, right? This was our v1, which went with lambda 1. And so again, I just want to make sure I'm kind of keeping these organized in my mind. 1, 0 is the x-axis. That's what I'm calling v1, and that was associated with lambda equals negative 1. This right here was our V2. That was with lambda equals -4. So here's kind of the thing that I'm seeing. If you go far away from the origin, what is really like the slope of this x to the fourth curve looking like? What's the slope of x to the fourth as you get really far from the origin? It should be almost vertical, right? And vertical is what our lambda equals -4 is saying to us. Our decay, when we're very far away from the origin, that e to the -4t is much more extreme than e to the -1t, and therefore that's the thing that's going to just shoot us down to the x-axis. But once we get really, really close to the x-axis is saying, oh, holy crap, I was supposed to be decaying also. Hold on, guys, we also need to go in before we go down any further and just touch the x-axis. That's not what's happening here. Our solution curves are not overlapping. So then once we got down closer to the origin right there, that's when it seems like the weaker of the two eigenvalues, the one that's not causing quite as fast a decay, that's where that one ended up taking over. And it looks like the slope that these curves all go into the origin at is the slope that agrees with the weaker of the two eigenvalues. So it looks like here our solution curves followed the weaker of the two eigenvector pairs into the origin. And part of the explanation for that is because of the fact that the stronger of the two decay terms out there was the one that was really dominant far away, right? When we're far, far from the origin at a time that's far away from zero, right? That's when our x to the fourth is almost saying go only straight down. And that makes sense to me because e to the -4th is way more strong decay than e to the -1. And so the decay was happening in the direction of the eigenvector associated with that -4 eigenvalue. But then because it brought us so far down vertically, it then needed to go in horizontally later. The weaker of the two took over later, and it followed the weaker of the two into the origin right there. V1 was the less extreme decay right there. That seems to be the one that was agreed with going into the origin. These solution curves out in space are matching the weaker of the two eigenvector pairs very, very, very close to zero. Very far away, it's the strong one that's dominant there. So let's go ahead and verify this with technology. So we need our system here was -1, 0, 0, -4. So let's go up top and change it. -1, 0, 0, -4. And let's, yeah, I want to do all my initial conditions out there, not just one of them. So we're good with that. All right, hopefully you feel really good about the graph that just got drawn right here. You should notice that a vast majority of the graph that you're seeing all is dashed lines because the solid lines represent forwards time. So from each of these 9 points right here, or I guess I'm stupid to have 9, the 8 meaningful points right here to go in forwards time was just to go to the origin because they're all a sink. The origin's a sink. They're all decaying towards the origin. To go backwards time would be going out from those points, which is why you're seeing almost all dashed lines. Other good things right here for validation is that all of our solutions in forwards time, you see the only solid line that you can see right here is essentially everything's zero because it looks like everything is decaying to zero. Both x and y values are decaying to zero as time moves forward right there. So these are both excellent justifications of the stuff that we saw right there. But again, the thing I want to say to you is this is not some algebra that we should rely on being able to do all the time right here. It worked out really nicely right here. And it answered a kind of weird question because in a sense, this is a crazy, easy, simple sink situation where you have just a diagonal matrix. I just get to read off my eigenvalues, get my eigenvectors. The two simplest eigenvectors that there could ever possibly be are two unit vectors, I and j, if you're a physicist or linear algebraist. But it wasn't super clear what those other curves should look like out in space. And so we kind of came up with a general rule that we think that we're going to see. It seems like our curves that aren't on the straight line solutions are going to follow our weaker of the two solutions very close to the origin. But let's go ahead and see this in a slightly more difficult setting out here. So let's go ahead and do example 4 with this D matrix here. This will be our last like sort of major example. I'm just going to show you what example 5 is. So check out our D matrix here, -2, -2, -1, -3. Our last example for the day is positive 2, positive 2, positive 1, positive 3. So for example 5, we're going to do essentially no work. We're just going to state that it's the opposite of example 4, and that'll be our last one. So this example 4 is sort of my last like real one that we want to look at here. But I want to show you some kind of complicated math that we can do to help us justify these types of conclusions that we just came at in example 3 right there. So again, you should now pause the video and see if you can do all the steps. Find your eigenvalues. Find your eigenvalues. Find your general solution. See if you can graph the phase plane right here. Can you categorize the equilibrium at 0? Is it a sink? Is it a source? Is it a saddle? Those seem to be the three that we came up with. We haven't even talked about source, but that's the opposite of a sink right there. I don't think anybody's going to have their minds blown about that one right there. The saddle's really the weird one of the day. So can we do all those things? And what we're going to see is this is sort of just like a harder version of the previous problem, but we're not going to get to be able to do this easy algebra here. So we're going to do something a little bit more crafty to convince ourselves of what the final overall phase plane is going to look like. And then once again, we'll validate ourselves with some Python code right there. So pause now and do this problem on your own. I mean it. Okay, now that you're on pause, let's go ahead and do this thing here. So I'm going to do all my same steps right here. I'm going to see how fast I can write my way through this, since none of this math is super, like this is very repetitive. This eigenvalue, eigenvector, general solution, phase plane thing. I mean, we're gonna do this so many times. So eigenvalues, determinant of d minus lambda I equals 0. That's our determinant of negative 2 minus lambda, negative 2, negative 1, negative 3 minus lambda equals 0. Oop, oop, oop. Determinant gives us a number. It's not a vector on the right hand side over there. So that's going to give me lambda plus 2, lambda plus 3, minus negative 1 times negative 2. I can tell I need to expand these quadratic factors because I didn't just get 0 right there. So I'm going to get a lambda squared plus 5 lambda plus 6. And negative, negative, negative is negative 2. Minus 2 equals 0. It looks like we're getting a lambda squared plus 5 lambda plus 4 equals 0. And what do you know? Lambda plus 1, lambda plus 4 is going to be a good factored form. And we're finding that lambda equals negative 1 and negative 4. And by the way, what were our eigenvalues in the previous problem? Oh yeah, they were negative 1 and negative 4. Right, so obviously these examples are set up to kind of like mimic each other, but be an easy version and a hard version of the same sets of eigenvalues right there. And again, I can't see the negative 1, negative 4 in this. I can't just like look at that and be like, I believe these are the eigen. I gotta know. I gotta write out this math a little bit right here. I think if I tried really, really, really hard, well, not even really hard, I could stare at this for 30 seconds and come up with these eigenvalues. But this is one that's obviously worth writing out. A previous one, if you get a diagonal matrix, you got them right there. Right, this isn't a diagonal matrix. Right? So let's go ahead and get our eigenvectors now. Remember, this is always associated with our coefficient matrix minus lambda I times the eigenvector is equal to 0. This is when we get non-trivial solutions. So let's go ahead and do this here for lambda equals negative 1. I'm going to be getting, and again, I always look back to my previous eigenvalue work to help myself out with this one. I'm just using this little matrix right here and sticking in each of the lambdas individually. So I'm going to get negative 2 minus negative 1, negative 2, negative 1, negative 3 minus negative 1 times xy equals 0, 0. And this is going to give me negative 1, negative 2, negative 1, negative 2. I know that I'm on the right track because I got my redundant system of equations right here. And now I just got to ask myself, what is the xy pair that would be a solution, a representative solution of the line of solutions that we're getting? And again, I'm going to kind of do the same little like sort of trick that I did earlier, which is if there's a 1 and a 2, then I need a 2 and a 1 so that they can cancel each other out as long as they're opposite signs. So for example, if I made x positive 2, then I'd get a negative 2 here. Then I'd have to make y a negative 1. Or sorry, if I made x2, then I get a negative 2. So I need a positive 2 to cancel it out. So therefore, I'd have to make y a negative 1. I typically like my 1 term to be positive. So I'm going to go ahead and pick x to be negative 2, so that we get a positive 2 from the multiplication. Then y can just be 1, so that positive 2 and negative 2 cancel to give me the 0 that I want right there. So I think that I want to do x to be negative 2 and y to be 1. And I think that'll be my good representative eigenvector. And again, lots of different ways we could have written this one. As long as yours is a constant multiple of mine, then you are correct. Get our second one here. let's see, -2 minus -4, -2, -1, -3 minus -4, xy equals 0, 0. It looks like we're going to get 2, -2, -1, 1. And now we're back in our nicest possible setting right here. Our goal is to add together two products of numbers, ax plus by, and get 0. So we want ax and by to cancel. And what is a and b right now? Well, they're 2 and -2. Those cancel if we just leave them alone. And what number do you multiply by to leave something alone? And that's 1. So I'm going to pick xy to be 1, 1, so that we get one copy of +2, one copy of -2, add together to give us the 0 that we want. Again, we get the redundant matrix, which tells us that we are on the right track right here. So it looks like we've got our two eigenvectors now as well. So we can use these to state our general solution. And that should be our vector y of t is going to be k1. Let me scroll up a bare smidge here so I can see all my parts. E to the -t, -2, 1, plus k2 e to the -4t, 1, 1. As usual, let's go ahead and also write this in its expanded form right here. This is the same thing as x of t, y of t equals -2 k1 e to the -t plus k2 e to the -4t. On the bottom, we have one copy of this term here, so we're getting a k1 e to the -t. Oops, that's a 4, not a t. And we're getting one copy of this term here. So we're in a similar situation as we were in the previous problem. It's a little bit more complicated in both the respects, though. So now for the phase plane. Easy part is the straight lines are basically just our eigenvectors. The hard part, the other curves, everything that's not on our straight line solutions out there. So let's see what we've got right here. So what I am seeing for myself, we're going to want a little bit more room for this guy right here. We're going to do a little bit of slightly tough math. I'm going to give myself a lot of room right there. I'm going to do some slightly tough math to figure out exactly what these other solution curves are going to end up looking like. All right. So what I know so far is this. I know that out there in the phase plane where all my solutions live, the two eigenvectors that we got, we have two negative eigenvalues. So I expect everything to be decaying towards the origin right here. We've got decay and decay for our two exponentials. Our two eigenvectors where v1 is -2, 1. Let me just state this right here. Lambda 1 is -1. v1 was -2, 1. Lambda 2 was -4. And its eigenvector was 1, 1. All right, so I want to graph these two straight line solutions at least, and then we'll say the now what do we do part. All right, so one thing here is 1, 1 as a point right here. I just want to draw the straight line solution that is a straight line between this guy and the origin. So, oh, that's not it. Try that again. Gosh, it's so hard to draw diagonally straight lines. Okay. All right, so there is our V2. And I know that because the eigenvalue is a real number that is negative, it's going to represent decay directly towards the origin along this line. Similarly, we can go to the location -2, 1, which is right there. There's -2, 1. And I know that there should be a straight line solution through the origin as well as that point. So I'm going to draw my other one that's right here. I again know because I have a real valued negative eigenvalue that this should be decay directly towards the origin on this straight line solution. That's what makes it so dang special. But the question is, what do the other curves look like in space? Can we find an algebraic relationship between x of t and y of t? And I'm going to give an emphatic heck no right here. And here's why. What we had before was just two individual terms, and one was just the fourth power of the other. Do you see any natural way that I could write x of t as a function of y of t or vice versa? And I think that the answer is sort of obviously no. Like, I don't see what I would do to the x of t equivalent, because this is just a constant multiple, but this is not that same constant multiple because the k2s are going to be equal to one another. It doesn't seem like they have any very nice algebraic relationship that relates them, where I'm just like, oh, multiply one of them by 6 and you get the other. Square one of them and you get the other. I really don't have that for x of t and y of t here. So I really can't play this algebraic game where I'm like, oh, y is x squared, and so they all look like parabolas. Oh my gosh, like, we can't play that game right now, right? I'm not seeing that stuff right here. So the question is, which straight line solution do our curvy solutions follow into the origin? The last example showed the weaker eigenvalue, eigenvector in, which in our case here would be lambda 1 equals negative 1 is the weaker of the two, and that would be associated with the vector negative 2, 1. So based on the previous problem, I am thinking that our v1 vector is what they're going to look like near the origin. So that is suggesting to me that I think that I'm going to get maybe some shapes that look like sort of parabolic, but where the flat part is flat on v1, and where we're going to look vertical in the way that v2 is vertical in the long run far away. So I'm expecting us to get a very, very similarly shaped graph as the previous one, whereas before we had our sort of parabolic looking shapes right there. I'm expecting those to have just been like tilted to the side to be sitting on V1 rather than sitting on the x-axis right there. That's what I learned from the last problem that I'm guessing is true. My question is, can we do some math that shows this? So here's what I want to do. Here's what I'm thinking to myself. I want to think about all of these curves that aren't on a straight line solution. All the ones that are out here filling in all this other space. What I want to know is this. What I know is going to happen is this. I know that as time moves forward that we're looking at a sink right here because we got two distinct, real, negative eigenvalues. So I know it's going to be a sink. I know that they're going to go to 0, 0. That's not the interesting part. That doesn't help me figure out what these curves look like. What I want to know about is, what is the eventual slope of those curves? And let me scroll back up to our previous problem to show you what I mean. Out here, our curvy solutions eventually had slopes of 0. And you should notice that if things had gone the other way, if we had picked the alternative graph, this one that's sitting right here, all of these eventually had infinitely large slopes as we got close to the origin right there. That would be a good distinction, is what's the slope look like as time gets bigger and bigger and bigger of the solution curve. That can help me determine which of the two trajectories, which of the two straight line trajectories it's following most closely as it goes in towards the origin. So here, if I had found that the slope, the eventual slope near the origin of all the other solution curves was 0, I know that the v1 eigenvector line also has slope 0, so that would say to me they're following in the v1 vector, which is exactly what we had ended up concluding for this guy. So what I want to do here is I want to try and do some math to find the eventual slope of these two lines right here. So eventual to me is saying the limit as time goes to infinity. Slope, what's the slope of my curve? Well, that's dy dx. But you should notice here, y and x are both functions of time, so we're in fact going to look at dy dt versus dx dt to get the slope, the eventual slope of this thing right here. So let's go ahead and see if we can do this crazy beast right here. So what I want to know is what is the limit as time goes to infinity of the slope of our solution curve, which I'm going to write as dy dt over dx dt. That's really our dy dx, just with there being another underlying variable t that's associated with it right here. What this means to me is that I've got to go ahead and compute some derivatives of my two statements right here. So I'm going to do the derivatives first, and then I'll do our limit statement second here. So what is dy dt according to our solution right here? Well, dy dt, the negative is going to pop down here, and a negative 4 is going to pop down here. So it looks like we're getting negative k1 e to the negative t. Similarly, on the next one, all we're doing is just popping down the negative 4. So we're going to get a negative 4 k2 e to the negative 4t. Divided by, now we'll take the derivative of the x parts up here. So very, very similarly, we're going to get a positive 2 k1 equal to the k1 e to the negative t. Blech. Positive 2 k1 e to the negative t. And for our second term here, we're going to get a negative k2 e to the negative, sorry, negative 4 k2 e to the negative 4t. Oh, and that was a 4t there, right? Yeah, 4t. So here's what I'm going to do. This is clearly not a super simple limit to evaluate right here, so let's be a little bit careful. Let's remind ourselves of some of the things that we all hopefully learned in Calc 1 as to helping evaluate some limits right here. And so what I'm going to do is I'm going to go ahead and I'm going to factor out this e to the negative t. I want to factor out the least common multiple that they've got between the two of them. So I'm going to do an e to the negative t and an e to the negative t. It's on top and on bottom. What do I have remaining? Well, this gives me a negative k1 minus 4 k2 e to the negative 3t. And I've got a negative, or sorry, and that's going to leave me with 2 k1 minus 4 k2 e to the negative 3t. It looks like these e to the negative t's are going to cancel with one another right there. And now what you can see is as I evaluate this limit, there is no t stuff remaining in these two components. T is getting really, really big, and t is part of an exponential decay term. So this is really going to be equal to negative k1 minus 0 over 2k1 minus 0, which is, and then the k1s are going to cancel, and this is just going to give us negative a half. So what this is saying to me is that the eventual slope of all of these curves that aren't starting out on a straight line solution is negative 1/2. And what line has slope negative 1/2 right here? Exactly our v1 vector, which is exactly the one that's associated with the weaker of the two eigenvalues right there. So that is pretty freaking sweet right there. And further, you can show that if you are starting on this line v2, then your eventual slope is going to be 1 right there. I'm not going to show that right there, but you could set up another limit statement to show that the only ones that are going to follow in this thing with slope 1 are the ones that actually start on the v2 line right there. So again, here's what we just did. We just found the eventual, limit as t goes to infinity, slope, dy dx, but really dy dt dx dt, because we wanted to incorporate the fact these are functions of t. I took the limit as t goes to infinity by factoring out these e to the negative t's, and I found that eventually the slope of all solution curves that don't start on the straight line solutions are all going to have a slope of negative 1/2. And you should notice that the x value of negative 2 and the y value of positive 1 is exactly a line of slope negative 1/2. This is exactly the eigenvector straight line solution that all these things are going to agree with. So as I said a minute ago, I'm expecting to see all those x to the fourth looking things from the last problem are very similarly just going to be sitting on v1, because they will eventually have slope of negative 1/2 down here. Whereas in the previous problem, that actually was x to the fourth, and they all had slope 0, which was agreeing with that other flat straight line solution curve right there. How cool was that right there? This isn't a limit statement that I think you ever thought you would have taken right there. So this completely agrees. This eventual slope of negative 1/2 of negative 1/2 agrees with our suggestion from the previous problem. That in a sink or source, solution curves near the origin closely mimic the weaker of the two eigenvalue eigenvector pairs. Lambda 1 equals negative 1 is weaker than lambda 2 equals negative 4. And remember that v1 here was the negative 2, 1. That's a line of slope 0. All right, so last things I want to do here is I just want to state, again, since we had two negative eigenvalues, 0, 0 is a sink. We've already said it a bunch, I just hadn't written it. Let's go verify in technology that we're going to get the graph that we're expecting. So I'm expecting those x to the fourth looking shapes, but I expect them to be sitting on our V1 line right there. So they're going to be angled like this right here. So let's go ahead and throw this guy into Python right here. So what was our system? Negative 2, negative 2, negative 1, negative 3. Let's go ahead and do it. Negative 2, negative 2, negative 1, negative 3. Negative 2, negative 2, negative 1, negative 3. I'm going to keep all those initial conditions, so I think I'm going to just run. Oh yeah. Oh yeah. So again, what we're seeing here is this. Almost all of what you're seeing is dashed lines because my initial conditions start very close to the origin. They have to go backwards in time to leave the origin. Forwards in time is going towards the origin. We are seeing these parabolic type shapes or maybe x to the fourth type shapes, but they're sitting on those straight line curves that are associated. Their eventual slope there is that negative 1/2. What you can't see right here are my two straight line curves. I guess you can see one of them because one of our eigenvectors was 1, 1, so you do actually get the straight line curve that goes from negative 10, 10 up to the upper right there. There's our positive 10, 10. So we actually, by accident, we do see one of our straight line solution curves. The other one of slope negative 1/2 is the one that you can't see, but it's what this is sort of sitting on. So it's sort of like we took some parabolas and like skewed them in a sense right there. But we also skewed the x-axis from being here to being a line of slope negative 1/2, which is exactly the slope of our weaker of our two eigenvalue eigenvector straight line solutions right there, which is super cool. And again, you can see that everything's clearly decaying to 0, 0, meaning that it's a sink. This is clearly the individual solution graph of a sink. because everything went to zero as time went forward, and it didn't take much time, right? I mean, everything now again, you should see again. Look at our vertical axis measurement out there. It looks to you like it's at 0, 0. These are all their initial conditions were like 1, 0 and 0, -1 and stuff like that anyway. But it doesn't look like there's any real deviation from zero there. So this is clearly the individual solution graph of an overall sink, and it looks like we were correctly able to predict. Which of the two straight line solutions were going to be followed in. And so it looks like our general rule of thumb here is that in a sink or a source, you're always able to easily graph your two straight line solution curves. It is not always easy to graph your solution lines, but the curvy parts of them are a little bit less obvious. And the takeaway from the math that we've done here today, just by like example, we have determined that it appears that we are going to follow into the origin or away from the origin the straight line solution that's associated with the weaker of the two eigenvalue eigenvector pairs, the one that's the smaller number, basically. Lambda -1 is less extreme decay than lambda equals -4 right there. And so we do get exactly that kind of information right here. So this was cool. I really like this little limit problem that's right here, calculating the eventual slope of a parametrically defined curve. Eventual means let the time go to infinity. Slope means do dy dx since we're in an xy plane, but since y is defined as a function of t and x is defined as a function of t, we took their individual derivatives with respect to time and took that ratio right there instead and found that the slope was indeed exactly the slope of one of our two straight line solutions. Really, really cool right there. So example 5, I know how long this video is already right here. All I'm going to point out is note that E equals -d. So I'm not even going to do this problem. I'm just going to say, obviously, these coefficients are just the negative of the coefficients from the previous problem. If you do the math, you're going to find that our eigenvalues are 1 and 4 instead of -1 and -4. Our phase plane, our eigenvectors are going to be the same. Our phase plane is going to be identical, except if we draw the arrows, all the arrows should be moving away from the origin instead of towards the origin. Let's just super quick go over to Python and see that, and then we'll summarize and call it a video here. So all I'm going to do is just get rid of the negatives on these terms right here. Rerun everything, and boom, we get the exact same graph, but the solid and dashed lines have switched where they're at, meaning forwards time is to go away. Forwards time is to go away. Backwards time is what would actually suck us back towards the origin right there. So let me go ahead and throw this guy in here. I don't think I need a very big version of this guy. Let's make it smaller. Hey, get back here, thing. Come on, Microsoft Word. You guys know what problems I'm having right now. Microsoft Word being crazy, dragging things all over crazy places. Come on, you're really gonna make me put this on the next page? That's a jerk move right there. All right, so there we are. So we got our phase plane associated with this guy here. So in general, classifying equilibria, we have two non-zero, real, distinct eigenvalues. Remember, if you get an eigenvalue of 0, all this stuff goes out the window. If you get imaginary numbers, all this stuff goes out the window. If both your eigenvalues are exactly the same, even if it's +3, we're still going to kind of get some like slightly weirder stuff going on. So they have to be distinct from one another for us to be able to draw these general conclusions here as well. So what we want to say here is if we get this lambda 1, lambda 2, I'm going to type out some stuff right here. If we get that lambda 1 is less than 0 is less than lambda 2. Oh my gosh, I can't type. Then we're going to call this guy a saddle. And we're going to say there is one straight line solution that tends to 0, 0. All other solutions come from and go to positive plus or minus infinity. If we get that lambda, oh my gosh, lambda, oh my gosh, lambda 1 is less than lambda 2 is less than 0. It looks like they're both negative, so we're going to get a sink. All solutions tend toward 0, 0. And all solutions not on equation. I need accent. I need this one. Oh, come on, get in there. Get in there. V1 will follow in V2. All right, so this is sort of they're going to follow in the weaker of the two. You should notice here that lambda 2 is the one that I'm saying is closer to 0 than lambda 1 is. So lambda 2 is the weaker of the two eigenvalues. So it's going to follow in V2, which is the weaker of the two the eigenvector associated with the weaker eigenvalue. Finally, for our last one here, I think that you guys are down with the fact that I'm going to copy and paste this whole thing because we're just going to make our source statement here. So now all I got to do is say, I got to just swap our role right here. Lambda 2, I'm going to say 0 is less than lambda 2 is less than lambda 1. And so notice here, I'm saying that lambda 1 is the dominant eigenvalue and lambda 2 is the non-dominant eigenvalue here. Or lambda 2 seems to always be the one that I'm referring to as being the lesser of the two numbers here, the one that's closer to 0. On V1 will follow V2 away. So I'm just going to kind of state this right here. All right, so this is sort of our conclusion for our classifying equilibria when we have two non-zero, real, distinct eigenvalues, very, very specific right there. We're going to get all of our other cases coming up here in the next couple days. So as my last departing statement to you, I do want to say I'm not going to do anything more right now because I know how dang long this video is right now, but the one thing we didn't do today is do some interpretations, some like real world interpretations about these solutions right here. So I would very, very strongly recommend you at least go to the book to check out our interpretations associated with Bob and Paul's CD stores right there. They make some statements saying, oh, if our X's and Y's represent Bob's profits and Paul's profits for their two separate CD stores, given that their initial profits are these and that their ABCD coefficients are these, what's going to be the eventual thing that's going to happen? Are they both going to make $1 million? Are they both going to go out of business? Is one of them going to make money for a while, but then they go out of business and the other one makes money? What's going to be the long-term trend associated with profits with their stores? The book does a really good job of kind of following along this like same question over and over and over again. So I'd very strongly recommend that you go and check out the interpretation at the end of this section right here associated with their Bob and Paul example where they do a little bit less of the math and do a little bit more of the interpret this in the context of a problem kind of thing in terms of profits associated with this system of differential equations. So that wraps up what I've got for you guys today. You guys, I think your takeaway statement from today's video should be, holy cow, that was a whole lot of math. And what I'm going to say to you is my departure statement for today is tomorrow we're going to do even more math. Our complex eigenvalue situation is going to take, I guess it's going to take exactly the same amount of math, but it's going to be about twice as much writing. And we're going to see a very good reason why when we talk about how should we be expressing our complex solutions. So we're going to get a little bit of extra hairiness considering we're going to deal with our imaginary numbers in our next video. I is going to be cropping up. You guys know that it's completely reasonable to get a quadratic characteristic polynomial and then there to be no real solutions. We're getting negatives in our discriminant there. And so we're going to want to be identifying how do we give, does it even make sense for us to give complex valued solutions to real valued problems? Should we just discard them? And we're going to see some pretty cool stuff pop out from these guys and some very cool phase planes pop out from these guys as well. Look for another video very similar to this one for 3.4 where we're going to do a lot of math once again and get all of our classifications associated with when we will see complex eigenvalues. I will see you guys for our 3-4 video. Have a good one.